That's it for static and kinetic friction. And one thing that's interesting is if we were to show a graph of static versus kinetic friction. I want to show you guys a graph of what it looks like, because it's pretty interesting. Let's say I have a graph like this, where on the x-axis we have F push, the force that I'm pushing on my calculator, for instance. And in the y-axis we have F friction, the force of friction acting on that calculator. As I said before, the static coefficient of friction, as I said before, the static frictional force is going to be scaling up as I keep pushing on it. And actually it's going to be a linear relationship just like this. Until we get to the point right here. And the thing that's special about that point, we call that Fs max, the maximum static frictional force. In the example I just gave, that was at 5 newtons. After which point the calculator starts moving and we're getting into the kinetic region. Interestingly enough, maybe you've noticed this before, but when you're pushing on a heavy box, have you ever noticed that it's actually easier to keep the box moving once it's already in motion? If you haven't realized that, you haven't pushed enough boxes in your life, well, that's fine, I don't really care. But yeah, that's what's going on. And the reason for that is the kinetic frictional force is constant, but it's also less than the static friction. It's constant, it's a straight line, but it's less than the static friction. In other words, as soon as you get over that initial hump of energy and force needed to make the thing moving, it actually gets easier to move once it starts moving, which I think, you can't deny that. That's pretty cool. And this is what the the graph looks like. We have the static region on the left, we have the kinetic region on the right. And remember, static friction is less than or equal to the coefficient of static friction times the normal force, while kinetic friction is always equal to the kinetic coefficient of friction times the normal force. And one thing, there's 2 observations you can make from this that are pretty cool. So first of all, mu s, I'm just going to tell you right now, is always greater than mu k. In other words, the higher the static frictional coefficient, so like the higher mu is, the more friction there is. And so if you're on something like ice with very little friction, you're going to have a very small value of mu. And what that also means is, since it's harder to get the object starting moving, since it's harder to get over that static frictional coefficient, mu s is higher than mu k. In other words, there's more friction before it starts moving. After you start moving the object, there's less friction. And it's because of these coefficients of friction. Pretty cool, right? Yeah. And the last thing I did want to mention is that, well, we have an equation for frictional force, for kinetic frictional force, right? It's just mu k times Fn. If this less than or equal sign, we can't just set it equal to mu s times the normal force, because that's a less than sign. It's not an equal sign. There's actually only one time, exactly one point, where the static frictional force is exactly equal to mu s times the normal force, and we can actually plug it into an equation. And the only time we can do that is at this point right here, Fs max. When we're talking about the max static frictional force, that's the only time it's equal to mu s times the normal force, the max static friction that it can handle. After which point, once again, it goes to kinetic, and the rest is history. So now we're going to get into some example problems with friction, static, and kinetic. Make sure you stick around and click on the next video. If not, it was nice joining you. My name is Dan the Tutor, and yeah, that's it.